introduction for Brill Noether curves.
Well, thank you for the introduction. So, basic question is this: if I'm writing at this size, can people in the back see fine? Great. The basic question I'm going to discuss today is when can we pass a given type of curve through a given number of general points. So this is one of the oldest problems in mathematics, and the first person to write about this was Euclid. Who knew the answer to this question in two different cases. And so there's the first postulate, which says that if I have 2 points, then I can find a line that passes through them. The type of curve is lines. They can pass through 2 points. And there is, there's proposition 5 of book 4, which says that if you give me any 3 points in the plane that are not all collinear, that I can find a circle that passes through the 3 points. So circles can pass through 3 general points. In this case, we can be more specific. The points have to be not collinear. And so the study of interpolating curves through points in antiquity culminated the work of Pappus at Alexandria, who showed that a conic section can interpolate through 5 points. And if I include degenerate conic sections, then I don't even need to say that my points are general. So this might seem well, hopefully I'm going to shortly convince you that this is a straightforward problem with modern tools, that a conic section can pass through 5 points. But you have to remember that back in the day, the question would be something like, you give me 5 points in the plane, and how do I, with a compass and straight edge, construct the 2 foci of an ellipse that's gonna pass through them, right? Which is not trivial, but doable. So let me explain now how to reprove this result of Pappus in a very easy way. So what is a conic section? Well, I can forget all about foci of ellipses and all these things, and I can just say, well, a conic section is something that I can write as ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. And this passes through a point xi comma yi if and only if, well, I just substitute in the point into the equation of my conic. And now you see, if you give me xi and yi, and you're asking for the values of a, b, c, d through f, a, b, c, d, e, f, this is a system of 5 homogeneous linear equations in 6 unknowns. And therefore it has a non-trivial solution, i.e. there is a conic section through these 5 points. So this is the key realization that was made in the 18th century. Basically that curves have equations, and we can study the ability of curves to pass through points by studying their defining equations. This is, in some sense, the birth of algebraic geometry. And so a couple of results from this era. Well, there's theorem of Kramer. This is the Kramer of Kramer's rule that from linear algebra. So 1750 that plane curves of degree n. So by that I mean that this is a plane curve of degree 2. I just mean a polynomial in x and y where all the exponents add to at most n. Okay, so plane curves of degree n can pass through n times n plus 3 over 2 points. And there's another result from this period that I'll mention is a theorem of Waring in 1779. And what Waring was studying was graphs of degree n polynomials in one variable, so something that looks like y equals an x to the n plus a1x plus a naught. And he showed that these can pass through n plus 1 points. In fact, he gave an explicit formula for a polynomial of degree n that passes through n given points. And in his honor, we call this the Lagrange interpolation formula. Okay. So one could probably give a whole talk about generalizations of the Lagrange interpolation formula and various applications of it to, real-world problems in coding theory and cryptography, numerical integration, and other things. But that's not this talk. Okay? This talk is going to be about generalizing results on the interpolation problem into higher dimensions. Okay? So are there any questions on what the basic problem is of passing curves through points? Are we all on board with that? Okay. So, if I give you lines, I can pass lines through 2 points, I can pass circles through 3, etc. But if I didn't know that already, how could I predict that? And so I want to introduce the notion of a dimension count. So let's say I want to describe lines. Well, I could define a line like so, and now I can count, how many coefficients did I have to give you in order to specify a line? Okay? So this is there's a two-dimensional space of lines in the plane, and lines can pass through 2 points. Right? Similarly, if I look at circles, well, I could write that as y, x minus a squared plus y minus b squared equals r squared. And now you see I have to specify 3 numbers. There's a 3-dimensional family of circles, and they can pass through 3 points. Similarly, conics. Well, to specify a conic, I'd have to write this. And it looks like this is 6 parameters. But it's really only 5 parameters, because if I multiply all of these parameters by 2, let's say, then I get the same conic. So it's really this mod scaling. Okay? And so there's a 5-dimensional space of conics, and I can pass a conic, again, through 5 points. So this is not a coincidence. And let me spell out why. So let's consider for a minute the space of conics. So this is some 5-dimensional space. All right? And each point in this space parameterizes a conic in the plane. And so this is dimension 1. So instead this is dimension 5. And now I have the space of So here's my space of n-pointed conics. Okay, so each point here in this space is parametrizing a conic together with a collection of points. And here's my space of n points in the plane, and I'm going to start using the projective plane here as my plane. So, a point here is just parametrizing my collection of points. And I have maps like this, right? And so this is dimension 5. And if I want to specify n points on this conic, which is a curve, then it's going to take me n more conditions. So this will be dimension 5 plus n. And now this is dimension to specify n points in a two-dimensional space. This is dimension 2n. And so what does it mean for, where should I put this? So to say that conics interpolate through n points, well, that's the same as saying that this map pi, which of course depends on n, is dominant. Dominant is algebraic geometry speak for basically surjective apart from something that happens when the points are not in the general position. Okay? And so, look, if this map pi is dominant, then the dimension of this space better be at least the dimension of this space. Otherwise, there's no way it can dominate. So we must have that 2n is at most n plus 5, and this is the same thing as saying that n is at most 5. So you see right away that I cannot hope to interpolate through more points than the dimension of the space that parameterizes the curves in question. And what this is saying is that this is always giving the right answer. So I now want to go back to our main question of when can we pass a given type of curve through a given number of general points. And to answer that question, we're going to first have to ask, what types of curves are there? So I'm going to give you a type of curve, and I'm going to ask you how many points it passes through. So the first question is, what are the different possible types of curves that I could give you to ask the question? So there are several important invariants of curves. So there's an intrinsic invariant called the genus of a curve. So there are several, probably the easiest way to explain this is to say I have some system of polynomial equations. And I'm going to look at the solutions to this system of equations, not over the real numbers, but over the complex numbers. And if I look at the solutions to the system of equations over the complex numbers, then they form some one-dimensional complex manifold. It's a real two-dimensional manifold. And now, what I do is I count the number of holes in this two-dimensional manifold, two-dimensional real manifold. And that's a topological invariant called the genus of this curve. There are also some extrinsic invariants of a curve. So here's my curve sitting on this curve C, sitting inside of some r-dimensional space. Well, then I have these two extrinsic invariants. So what is R itself? This will be the ambient dimension. And the other is what's called the degree of this curve. And so if you take a hyperplane, so this is something defined by a single linear equation, then you can count the number of intersection points of this curve with this hyperplane. And I want to work over an algebraically closed field when I do this. And so D will be the number, so we'll call this hyperplane H. D will be the number of intersection points of C with H. So if you're like imagining drawing this curve here, you'd be counting, and looking at it, you're sort of counting the number of times the curve crosses the horizon. So let's say a few words about what we expect the answer to this question of interpolation to be. And it will be a souped up version of this diagram. So I have curves, and so first what I can do is I can take the space of curves of genus G, just intrinsically. Okay? So this is space called MG, and the points, each point here corresponds to a curve of genus G. And now what I can do is I can look at how these curves are embedded into projective space of some dimension. And so this space, here's my cartoon, okay? So this is my cartoon picture of MGPRD. So what the points of this space parameterize an embedding of a given curve into projective space. And I've drawn this as a somewhat funny looking space, whereas I've drawn this as a nice looking space, and that's intentional. Okay? And so we'll say, okay, well, this will have some dimension. And then well, let's see. Okay, so let me try to do this. Imagine for just a moment this board is on top of the other board, and then a minute later I'll make it so. So, now I can consider the space of m-pointed curves embedded in space, which I might draw like so. So this is my cartoon picture of MGN PRD, and what this does is that each point on it parameterizes a curve with m points on it, and this will be dimension, whatever the dimension of that space is, plus n, because I have to pick my n points on this curve. So and now I have this map pi from this space to the space PR to the n. Okay, so a point in this space parameterizing n points in an r-dimensional projective space. And so what do I expect? Well, I expect that pi is dominant, which is, of course, the same thing as saying that C pi my curve of this degree genus interpolates through n points, if and only if, well, the dimension of this space up here is more than the dimension down here, i.e., times n is at most, whatever this question mark is, plus m, or stated a different way, r minus 1 plus n is at most this dimension. Okay. So what is this? What is this dimension here? Well, as I've drawn this space intentionally, there are multiple different components. And these components have different dimensions. Okay? But there is one nice component that maps nicely onto the space of intrinsic curves. Okay? And so this is the subject of what's called Brill Noether theory. And so let me state the following theorem, which is due to joint work of many people, including Griffiths, Harris, so it's not that all of these people co-authored one paper together, but that there's the proof of this theorem is scattered over many different places in the literature. Each of these people proved a piece of this. So these are probably, if I had to pick 6 names, I'd pick these 6, but there are others involved too. Okay, so the theorem is the following. Let C be a general curve of genus G. Then C admits a non-degenerate map of degree G. So non-degenerate just means that the image of the map is not contained in a smaller dimensional projective space. In which case, really, you should just be thinking about the whole problem is taking place in a smaller dimensional projective space. Okay? So it admits a non-degenerate map of degree G to projective space of dimension R if and only if this quantity known as rho of GRD, which explicitly is G minus R plus 1 times G plus R minus D, is greater than or equal to 0. And furthermore, in this case, the universal family of such curves is irreducible. Of dimension as so. So, what we're saying is that there may be many different components of the space of curves of degree D and genus G in an R-dimensional projective space, but most of the components do not dominate MG. Most of the components map onto something smaller dimensional here. And there's only one component that spreads out nicely over the entirety of MG. And I know its dimension. And so, definition, we'll call such curves Brill Noether curves. Chalk, I'll just call them BN curves. Okay, so we're going to ask not when is there a curve of this degree in this genus through this many points, but when is there a Brill Noether curve? A curve corresponding to a point of this nice component. So we're asking when does this nice component dominate PR to the end? So, not what I should have erased. Okay, well, here we had this equation, right? And so, what erased is this? So, the basic conjecture you might make is, suppose on integers g, r, d, and n, where rho is non-negative. That's the condition that's necessary for this Brill Noether component to exist. All right? So then, we can pass a Brill Noether curve of degree d and genus G through n general points, P1 and Pn, and PR, if and only if this condition here is satisfied, that R minus 1 n is at most this dimension So that's what we would expect on basis of a dimension count. And it's maybe worth pointing out a generalization of this that you can work out with a very similar dimension count. I'll call this, well, we'll call this conjecture 1, and we'll call this conjecture 1 plus epsilon, that you could similarly ask, rather than passing through points, you can ask the question about meeting general linear spaces. So I give you a collection of, I give you a point and a point and a line and a plane and something. I ask, well, is there a curve that meets all of these linear spaces? Touches them. So you can meet general linear spaces if a very similar sort of inequality holds that comes from a very similar sort of dimension. Okay. Are there any questions? Yes.
Can you clarify what exactly you mean by a curve? So, like, are you looking at all possible continuous functions from an interval into RD, or are you requiring them to be like algebraic or something?
I'm looking at algebraic curves.
Okay.
So,
All right. And when you say
of a given degree and a given genus.
okay, can you clarify also what exactly is the genus of the curve?
Yeah, so if I describe my curve as a solution set to a system of polynomial equations, I look at the solutions to those equations over the complex numbers. Now I've got a one-dimensional complex manifold. That's a two-dimensional real manifold.
Okay.
And it's a many-hole torus, and I'm counting the number of holes.
All right. Okay, I see.
Okay?
Yep.
Yes?
How does this component of MG-PTRD compare with the other components? Like, is it the largest component when it exists, or?
No, it's not necessarily the largest component. There can be other components that are larger. It's just that the other larger components get highly collapsed under this map to MG. So there's only one component that sees most intrinsic curves of genus G. Does that answer your question?
Yep, thanks.
So in fact, there are examples where there are other components of this space that are larger in dimension than this Brill Noether component, and which dominate PR to the n, even when the Brill Noether component does not. Okay? So this really does change the question. It's a different question to specify that the curves that we're considering are Brill Noether curves.
So when you say the Bn component does not dominate MG,
No,
sorry,
the Bn
does not dominate PR to the n. It's when this condition fails, I guess. So
Hold that. We have a conjecture.
Okay.
The conjecture is saying that. Okay. Are there other questions? Yes.
Let's see. When is dominant? Will you have any information about which points are missing? Which n-tuples are missing? Do you have any way to get information?
That's very hard.
Okay. And also, are there any reality issues here? Like, right? I mean, presumably, was it Pappas? We're talking about real
right.
conics?
Okay. So we want to talk about over the complex numbers or over some algebraically closed field. Yes.
So you don't want to answer the question.
I'm not going to answer that question.
Okay.
I'm not going to answer that
Just
question.
clarifying. Yeah.
Okay.
Why is this number,
Yeah.
so the number on the bottom left word, I would have thought it should be 3g minus 3 plus rho. So
It's not quite.
so why
It's
why
3g minus 3 plus rho plus the dimension of the automorphism group of projective space.
I see, okay.
Are there other questions? Yes.
What is the significance of the number rho? Like, where does it come from? What is it measuring?
Well, it is, if I have a line bundles of degree d on a curve, as like the data I need to define and map to projective space, there's a g-dimensional family of those line bundles. And to have a map to projective space, I need to have this dimensional space of sections. And by Riemann-Roch, that tells me this is the H1 of the line bundle. So that's how you can think about this number. Are there other questions? All right. So we have this beautiful conjecture, or beautiful pair of conjectures. And so the next thing to discuss is some counterexamples. Okay. So
Is that your conjecture?
what?
Is that your conjecture? Is that your conjectures?
Is this my conjecture? I mean, I would say it's to some extent of well, it's a natural conjecture one might make, but the problem is that you would find counterexamples to it very rapidly. Okay. So here's the conjecture. Now let me tell you some counterexamples of the conjecture. So. Here's one counterexample. Curves of genus 4 in P3 of degree 6. Okay? Now, every such curve turns out to be the intersection of a quadric surface and a cubic surface. And if you do a dimension count on space of quadric surfaces in P3, you will see there's a 9-dimensional family of them. And a similar sort of dimension count will tell you that similar dimension count will tell you that this can only pass through 9 points. Okay? But the conjecture is saying that such curves should be able to pass through up to 12 points. So they can't. Because certainly the dimension count is a necessary condition. Another counterexample in a similar vein.
So what would the conjecture say in this case?
So if you work out the bound on
Oh, it's
n,
at 12, sorry, okay.
from this, the conjecture says that n should go up to 12.
Sorry, yeah.
Is
Yes.
this one of those cases where there's an extra larger dimensional thing that
Nope.
covers? It's not.
Well, this is all happening with the Brill Noether component.
Yeah, I'm just asking whether there's another component that maybe does the job. Not even. Okay. It's fine.
So in this case, the space only has one component. That's the Brill Noether component. All right. So here's another example, and this is a curve in a 5-dimensional projective space, and it's the intersection of a quadric surface and this quadric hypersurface with a surface that's called a quintic del Pezzo surface. And this quintic del Pezzo surface can only pass through 11 points. Even though the conjecture, again, in this case, allows n to go up to 12. So here's another counterexample. But that's not all. So here's a couple of counterexamples. Finite number, but they sort of come together naturally in this family. So let's look at this. So I have a curve, genus 2, embedded in the projective space of dimension r. And one thing about curves of genus 2 is that they're what's called hyperelliptic. There's a natural involution on them. And so I can take pairs of points of this curve that are conjugate under this involution. And I can join them with lines. And these lines sweep out some surface, which I'll call S. This is an example of a scroll. And the dimension of the space of such scrolls is r squared plus 2r minus 6. And so now, you can make a little table. So we look at what the conjecture predicts. And we can compare it to the maximum allowed by this scroll. So I can do a similar dimension count with this dimension of such scrolls. Okay? So we can look at R as 3, where the conjecture predicts that n should go up to 10, but the maximum allowed by the scrolls is n up to 9. You can look at R equals 4. And here the dimension count predicts n up to 9. And the maximum allowed by the scroll is n up to 9. So it looks okay. But if you look at conjecture 1 plus epsilon, in fact, conjecture 1 plus epsilon should predict that you can pass up through 9 points and meet a line. And here you cannot meet a line. You do not have enough dimensions for the scroll. And you can look at R equals 5, where this conjecture predicts n up to 10, but the maximum allowed by the scroll is n up to 9. So these are counterexamples to conjecture 1, And this is a counterexample to conjecture 1 plus epsilon. Okay. So it's now 3:56. So I'll finish the talk, the theorem statement. This is due to joint work of myself and Isabel Vogt. And the theorem says that conjecture 1 plus epsilon holds except in these 5 cases. So there are these 5 cases where there's some exceptional geometry. And in every other case, this naive dimension count correctly predicts the number of points that you could interpolate curves through. Okay. So I'll stop here and ask if there's any questions. Some questions? Yes.
Can you say what goes into the proof?
Well, not in 3 minutes, but I mean, what I can say is, I can say a little bit. So there's a well-established strategy for studying problems like this, which is the strategy of deformation theory, where you take a curve and you take some points on it, and then you try to move the points and see how the curve can deform with the points. And that's also the approach that that we take. But what that turns the problem into is basically a problem about analyzing the normal bundle of this curve in projective space, which controls the deformation theory. And I can certainly say more about how to analyze the normal bundle, which is our main contribution here. But that's probably going to take me more than 3 or 4 minutes, and so maybe what I should do is take other questions first, and then if you want me to tell you something about that, I'm happy to do that after people have had a chance to leave. Are there other questions? Yes.
So is there any kind of intuitive or relatively easy to explain intuitive explanation for why these should be the only 5 counterexamples? Is there some other known result that these are the only 5 examples that satisfy something?
Nope. It's you have to try to prove the theorem, and you have to keep searching for counterexamples. And at some point you hope that you manage to make these things meet in the middle. I mean, it's not. There's no magic trick that explains these 5 counterexamples.
Maybe
Yeah.
let me just rephrase that question as well. Do these counterexamples come from your proof, or is the other way? This counterexample before you give the proof of this?
Well, I mean, I can tell you historically that we considered some of these counterexamples because we were noticing that our proof was not working in these cases, and so we
So in some sense, come from the.
But the arguments for these counterexamples are very much simpler than the proof. So it's not.
Can your theorem be generalized to embedding curve into some Grassmannians?
Well, so I have another theorem which is joint work with Isabel and Izette, Isabel Voden is at Joskin, that will, in the case where G is 0, will, as a consequence, almost answer this question for curves and Grassmannians, but not quite. By almost, I mean that I can give you a number, and the number is off by almost 1. But then there are examples where the number is in fact off by 1, and we have a more precise conjecture that now there are infinitely many counterexamples, so to speak. But we can talk about that more. Also, that's another longer question. But I'm also happy to say more later.
It looks like there's a sort of a common feature, which is in one case you're splitting it up into two curves, and the other one you've got something it's inside of.
Well, so in all cases, there's something that's inside of, right? Because you see, these curves are inside of this scroll. These curves are inside of this critique del pezzo surface. The quadric is just going along for the ride.
Oh, well, that's right. So
This is inside the quadric. The cubic is not.
So it's just a
going
bigger,
along.
right? You're
So
only
in all
using the larger one.
In all of these examples,
So are there other examples, but they don't somehow match the
Every-
lots and lots
every curve lies on lots and lots of surfaces. The question is whether, due to its exceptional geometry, you can find such a surface that obstructs, that moves in a small enough dimensional family as to obstruct this.
of. I see. Yeah. So you're trying to find something that's bigger than it, that's somehow smaller in this other sense.
Exactly.
Not cooperative in this other sense.
Yeah.
But first you replace it by something larger.
So if you prescribe singularities, order of singularities in these points through which you pass your curve, so even in dimension 2,
Well, even in dimension 2, that's an incredibly difficult problem.
so that's Nagata conjecture kind of.
Yeah.
Can you advance it with your tools?
No, the argument that goes into this theorem has nothing to say about Nagata's conjecture. Yes.
Can we say anything about the uniqueness of like the, I guess like points and interpolation?
The uniqueness of the curve that passes through them?
Yeah.
No, we cannot say anything about the uniqueness. I mean, apart from a dimension count that tells you that in certain cases the dimension is positive and so it cannot be unique, but in no interesting cases can we say anything about the uniqueness. Yes.
It's only over the complex numbers or any algebraically
This is over an
closed field or
algebraically
any
closed field of any characteristic. And there's I briefly alluded to something about the study of a normal bundle. And it turns out that for the analogous question about normal bundles, there are additional counterexamples that appear in characteristic 2, but that don't get reflected in this statement. So that's another, if you're curious about that, I can also talk about that afterwards and hang around, but that's a longer digression. Other questions?
So, more questions? Let's thank the speaker.